This one is problem 1.24. This is for building construction, where we use this setup for leveling up. So in this one, there's a temporary column right here, which is this one right here, and this is being supported for a weight of 10 kilonewtons, and there's a wedge that is being driven inside with the hammer from this side B. So when this wedge goes inside, this point C is slightly lifted. So what we need to figure out here is we need to estimate the minimum force between the hammer and the wedge, which will cause the wedge to move further in, assuming all coefficients of friction as 0.3. So we have to figure out, when this is being pushed in, what should be the minimum force required from this hammer P. So for this purpose, we will draw the free body diagram of the rigid bar AB and the wedge. Now since this wedge is moving in, the motion is happening leftwards, so the friction at this contact and this contact, both of these contacts, because friction always opposes the motion, so it should be opposite to the motion. So if this motion is to the left hand side, your friction force is going to be to the right hand side. So in terms of friction at both of these spots, your friction is going to be this way. Now at this contact point, if friction is pointing this way here, and this point, your friction will be this way here, and there will be a normal contact force on the bar this way, and there will be a normal contact force on this one here, and there will be a normal contact force which is at the ground also. Now to name these, we call this FB, this is also FB. Now if the coefficient of friction is F, this become F times FB, and this is also F times FB. Let's call this FC, and this one as F times FC. Now at this corner here, because the motion is restricted from both sides X and Y, there will be two forces. This one is FAX and this is FAY right here. Now since the wedge is at 30 degrees here, so this angle is 30 degrees. So here also this angle is going to be 30 degrees. The load that is supported will be acting right here at the center, which is 10 kilonewtons, and these distances here are 0.5 meters and 0.5 meters right here. Now this angle right here, because it's a very small angle, we can assume this to be very close to 0. Now let's do the moment balance for the bar about point A here. So this 10 kilonewton will give you a clockwise movement, so 10 kilonewtons times 0.05. Now these two here, if this angle is 30 degrees, your FB cos 30 will give you anti-clockwise movement, and this will be at a distance of 0.5 and 0.5 years, so 1 meter. And similarly this F times FB, this will have a sin 30 component which is vertical, again sitting at a distance of 1 meter, and this will also give you a clockwise movement because force is downwards. So all of this is equals to 0. Now everything is known in this, so if I substitute all the values and solve for FB here, the value of FB from this comes out to be this minus F, and when you simplify this, this is 6.98 kilonewtons. Similarly, when I do the force balance for the wedge here, there is one force missing on this FBD, which is the force P that's coming from the wedge. So for the X force balance, we'll have F times FC, which is this force, plus F times FB cos 30, the X component of this, and FB sin 30, which is again for this force, there will be a horizontal component, minus P equals to 0. And in the y direction, we are going to get f times fb sine 30 minus fb cos 30 plus fc equals to 0. So there will be a y component from this, and this one. So when you solve for these two equations, from the second one, fc can be directly solved because fb is known, and the value of fc comes out to be 5 kilonewton. Everything cancels out, and then this comes out as a nice number. fb we have already calculated, which is 6.98 kilonewton. Now if I substitute these two values in the first equation right here, the value of p comes out to be 6.80 kilonewtons. So this force right here, this is the minimum required force that you need to apply from the hammer so that the wedge can go inside. Now for the second part here, it is asking what will happen if the coefficient of friction is too small. So when you apply this wedge force, this will be going in, and then because of friction, this will remain in place. And if there is no sufficient friction, this wedge will try to slip out. Okay, so when we try to understand the slip out motion, the tendency of motion for the wedge is going to be to the right hand side. So because the wedge is moving right, so now your friction directions will be exactly opposite to the case that we have already seen. So now with that in mind, if we try to analyze the slip out case, so in this case, your FBD right here, these forces will be as it is. FAX goes here, FAY goes there, your 10 kilonewton force is here, your normal reaction will also remain same, FB, but now your friction direction will be somewhere here, and this angle again is 30 degrees. Now if I draw the wedge forces, now this is the situation when we have removed the force P. Okay, now we are analyzing whether the block is going to be slipping or not. So at the bottom we are going to have this force FC, this FB will be as it is. Now friction direction, since it has changed here, this will be on this direction here, and similarly on this part the friction direction will be this way. Now this one, which P force that we had, since we are talking about the slip out case, we have already removed the force, so this value we are going to take it as 0. So like the previous case, now if we start writing the equations here, for the bar we will do the moment balance, and in that moment balance the first thing will be 10 kilonewtons times 0.5, this is 0.5 and this is 0.5, a clockwise movement. Now this FB right here, it will have a vertical component here and about this point A, and this will go in anti-clockwise direction, and this FB also here will, the vertical component will go in the anti-clockwise direction, so both of these will be negative, so we are going to get minus FB cos 30 sitting at a distance of 1, and similarly minus F times FB sine 30 at a distance of 1. So all of this needs to be equals to 0. So if you solve from this, your FP value in this case will come out to be 10 divided by square root 3 plus F. And since we are interested in finding out that particular value of F for which slip out will not happen, so we'll keep F as unknown here. Now from the forces on the wedge, you can see this angle is 30 degrees here. So if you look at your X forces, we have your minus FC, this one, minus FB cos 30 and plus FB sine 30 degrees, and since P is 0, that's, we can ignore it. In the y direction we are going to get this force, which is minus FB sine 30 degrees, this FB right here, which is minus FB cos 30, and plus FC equals to 0. So now there are these two equations. So from these two we can solve for FC, and more importantly we can solve for the value of F, and this will be the limiting value of F for which the slip out will happen. Okay, so if your friction is less than that value, then slip out will happen. If friction is more than that, then your slip out will not happen. So when you solve this second equation here, substituting the value of FB there, your FC directly comes out to be 5 kilonewtons, and when you put it back in the first equation right here, you're going to get one quadratic equation in terms of F, which is a friction coefficient, and there will be two roots to it. One of them will be negative. So friction, since it cannot be negative, the only positive root that you get for this is 0.27. So this value of 0.27 is, so if F is greater than 0.27, then block holds its place and there is no slip out, and if F is less than 0.27, then it's going to slip out, or for better, this is equal sign theory. Okay, so the borderline or the boundary case is when your F is 0.27.